Alright.
What else do we have?
Mr.
Next.
Milam,
What?
someone sprayed pepper spray in Canton.
Really? Was
Yeah.
it me?
In Canton High School. Were you in Canton High School like 10 minutes ago?
No, I never go to Canton.
But apparently
Canton
people are getting,
sucks.
like-
It's almost as bad as Salem.
Yeah, but people are like coughing up blood. I don't know.
Coughing up blood?
That's what Samira said.
That's what people get for peacefully protesting. Boom, politics. Alright, so
Broke down the
what I'm going to talk about for our final thing is called KSP.
low pH.
So,
Enough fueling explanation I have.
Akash has taught you all this stuff, I assume, about equilibrium. So you recognize this is equilibrium from the K. SP means solubility product, but basically to us that means salts dissolving in water. So I just want to go through a couple simple situations so you kind of have a basic idea of this. So silver chloride is an insoluble salt. When I say insoluble, that means for the most part it's insoluble. However, in real life, a very, very tiny amount of this will dissolve. So there's two different questions here. They might give you a question and say, what insoluble salt do you make? And you might say silver chloride, even though I'm about to tell you about how it dissolves a little bit. That's because the amount of these are so ridiculously small that if you mixed silver nitrate and something chloride, you'd form a precipitate. But when you form that precipitate, there will remain a very, very small amount of each of those in there. Yes.
Is there a number cut off between like being insoluble and soluble?
Not a good one. So for example, we were talking about phosphate. Sodium phosphate is considered soluble in water because all sodiums are. But when we make sodium phosphate, it's really challenging to dissolve it to make like, we do a 1 molar solution for one lab and a 0.2 for the qual lab. And even the qual lab 0.2, it doesn't all dissolve. Yeah. So think about that, qual lab fans. Alright, so here's the deal. Most of this is this, but this is a solid, and therefore is irrelevant to our equilibrium discussions. So we ignore the whole thing. So the only thing that matters here are the products, and hence the term solubility product. Okay, so the idea is we're going to start with nothing of each of those, and then a very, very tiny amount of this is going to dissolve. So overall, we're still saying it's insoluble, but we want to look at sometimes at how much these things actually do dissolve. So to do that, we note that anytime one of these formula units dissolves, we have to produce equal quantities of both. So when we don't know how much dissolves, we have a number letter thing for that, x. So what we would say is, however much each one of these dissolves by and goes up by, we don't know, but we know that they're going to be by the same amount. So at equilibrium, we will have X silver plus ions and X chloride ions dissolved in a liter of solution. Okay. Now the K value for each one of these at some temperature, we can then plug in to this expression. So the KSP expression for this is Ag plus times Cl minus. So at equilibrium, I would plug in X for silver, I would plug in X for chloride, so my KSP would be equal to X squared. Now here's the cool part. Whatever X is here is how much of this dissolves, right? Because for every one of these that dissolves, I get one of each of those. So if I know what X is, I know the solubility of this. Now what are your units for these charts for equilibrium analysis? Do you know?
Moles per.
They're molarity, or moles per liter. Okay. So when you're done, if you can solve for X, if they tell you the KSP, and you figure out that it's equal to X squared, you can solve for what the concentration is. It's going to be tiny. It's going to be like 0.0000 something. Okay? I think like the KSP for this is 10 to the negative 10th, somewhere in that ballpark. So then the concentration is going to be about 10 to the negative 5th, or 100,000th of a mole per liter. Okay. If you wanted to know grams, you could take X, and you could change moles to grams by multiplying by the molar mass. And then you would find out that maybe 0.0 this many grams dissolves in a liter. Okay. Now this has application to the lead stuff because we can take things like, say, lead carbonate, or lead chloride, or any other insoluble lead compound, lead sulfide. Any of those you could do a KSP thing for. However, you will find that one of these is a little different than the others. In this one, you're going to turn into a lead ion and a carbonate ion. In this one, you're going to turn into a lead ion and a sulfide ion. But in the chloride, you're going to end up producing a lead ion and 2 chloride ions. How will that affect your ice chart? So there's actually 2 ways. One is, let me do the whole thing again. So one is, now, instead of forming x and 2x, or x and x, you're going to form x and 2x. Because every one lead is accompanied with 2 chlorides. True? And then the other thing is your K expression is now going to be different. My KSP for this is going to be equal to my lead, but for my chloride, because there's this coefficient in front, it's going to be squared. So when I plug in x for this, and I plug in 2x squared, I end up with no longer x squared, I end up with something totally different. Now I end up with x times 2x squared, which ends up being 4x cubed. And I'll point out it does not end up being 2x cubed. Don't forget to square the 2. So here's the deal. Here are all the salts you could have. If you have a +1 and a -1 charged salt, you're going to end up with KSP is equal to x squared to get the solubility, in molar solubility. If you have a +2 and a -1, or a -2 and a +1, you're going to end up with KSP is equal to 4x cubed. Okay. If you end up with a +3 and a -1 charge, you're going to end up with 3x cubed, so you're going to end up with 27x cubed times x, so 27x to the 4th will be equal to KSP. And then if you have a +3 and a -2, your KSP will be equal to 27 times 8, times 4, which is 108 x to the 5th power. Now, you can't have a +3 and a -3 because that's just going to be 1 to 1. I mean, you could, but it'd be 1 to 1. It'd be just be x squared. Okay. So these are all the KSP expressions for the following situation. You put a pinch of really insoluble salt into water, and you want to know how much dissolves. There's one kind of contrary thing to that, and that is in the packet you picked up. Let's say I want to figure out the solubility of lead chloride, and I put it into a sodium chloride solution. The fact that there's already chloride there will actually greatly reduce the solubility of this, because watch the chart for this. So normally, if we did this problem and we didn't have chloride present, we would start with 0, we'd add x, we'd add 2x, end up with x, 2x, and so we'd end up with a KSP of this thing equal to 4x cubed. But let's say instead, now I'm going to dump this into a solution of 0.1 molar NaCl. What that does is instead of starting with 0 here, I would start with 0.1. And that's actually a huge change because 0.1 plus 2x, when x is really tiny, is effectively still 0.1. And when I plug in 0.1 into my K expression, now I get 0.1 squared times x. And 0.1 squared is going to be a lot bigger than what 4x squared would have been. And so now my solubility, my x, is going to go way, way down. Let's throw a number in there just kind of. Let's say that my KSP is 4 times 10 to the negative 12. Okay, so 4x cubed means that x would be 10 to the negative 4th here. But if I have a 0.1 there, then that means now down here, my x is going to be 4 times 10 to the negative 10. So you're seeing a difference in solubility by 4 million. This is 4 million times less soluble when I start with some chloride present. And that makes sense because we're talking about an insoluble salt, so having a whole bunch of half of that salt is going to greatly reduce the ability of a lead ion to escape that crystallization and go off in a solution. So anyway, this is KSP, that's it. There's, right, good. They can become challenging problems from that, but we don't need to go through that. But if you want to see a really challenging problem, that second packet, the fractional crystallization, is where you take 2 insoluble things, but only put the cations or only the anions into solution, and then you slowly add the opposite. So you could put like lead and silver into a mixture, and then very slowly add chloride to it, and see which one would precipitate first, and by how much, and all of that, and that turns into a hot mess of this stuff. So if you want to check that out, you're welcome to do so. I would wait for later on that one. Alright, cool? Done with Chem Olympiad? Who's the video for? Girlfriend.